Sir, sir,
Hi,
sir,
we'll be starting the session in a little bit. If you have any question, could you type it in the chat?
it's actually not a question, it was just a request.
Uh-huh, go ahead.
Can you keep it as simple as possible? Because I don't have any knowledge on this topic, so
Yes, of course, that's the goal of the session, and we'll try to keep it as interactive as possible and as simple as possible. And after that, if you have any question, then I'm sure that sir will be more than happy to address those. Okay?
okay.
Also,
Thank
also Dr. Nitendra is there and he makes things very simple. So
I'll
don't
try
worry.
my best.
Yeah.
All right. I think let's start now. How long is the session? We'll get back to you on that. Gia and Mrigdha, if you could respond on chat, that'd be good. Okay. Good evening, everyone. Welcome to the Karyo Summer 2026 Bootcamp. My name is Siddhi Kochar, and I'm the student head of Karyo Science Society. And I think I speak on behalf of the entire team when I say that it's truly a pleasure and a privilege to see so many students, educators, and science enthusiasts joining us today as we begin a very exciting journey together. At KaryoUS, we believe that science is most powerful when it is collaborative and and when it fosters active communication within our team. And in fact, our society was founded with the vision of fostering cross-campus collaboration among students of the Shimpanadar campuses and the Vidyagyan schools, creating a community where curiosity transcends the mere boundaries of schools and campuses, and students can learn from one another, exchange ideas, and contribute to society collaboratively. And so, through initiatives like in person residential boot camps and summer boot camps, we aim to bring students closer to cutting edge fields by creating opportunities and engaging directly with experts, researchers, and innovators. And more so than that, we hope that these conversations not only deepen your scientific understanding, but also inspire students such as yourselves to think critically about the challenges and opportunities that shape our future. And before we begin, I would like to extend a very warm welcome to our esteemed guest speaker, Dr. Nitendra Singh. Dr. Singh, thank you so much for taking the time to be with us today. We are incredibly excited to hear your thoughts and learn from your experience in the field of advanced
Audio.
technologies.
With pleasure. Thank you for having me.
I would also like to take a moment to express our heartfelt gratitude to our mentor, Miss Vinita Sharat. Her unwavering guidance, encouragement, and belief in us have been instrumental in shaping KaryoUS into what it is today. And even on a personal note, ma'am has been a constant source of motivation for me. And I know that I speak on behalf of the entire KaryoUS body when I say that her support has been pivotal and one of the driving forces behind everything we do. And so I seem it very fitting that before we begin today's session, I would like to invite Vinita ma'am to share a few words with us. Vinita ma'am?
Actually,
I think Vinita ma'am is.
it's not required. I just want to say, can you hear me?
Yes, ma'am.
So I just want to say thank you to all the teacher mentor, including the students lead from all campuses, Vidyagan and all SNS. Today SNU is lead is missing. This because there's a reason behind that. She has written a personal note. But a big thank you to all of you. There is always ideas do keep coming in my heads. But if you guys are not there, if you people are not there, the teachers, the student lead, this would not have been possible. So please go ahead. Thank you very much, Siddhi. Mayank sir, Rachna ma'am, Renu ma'am, all campus lead, Ravinder ma'am from Faridabad. So you all are amazing. Because of you all, this is happening. Thanks a lot.
Thank you, Vinita ma'am. And all right, perfect. With that, I would like to give it over to today's hosts, Mrigdha and Gia. Mrigdha and Gia, the floor is yours.
Thank you so much for that introduction. Good evening, everyone, and welcome to the first session of the Karyo Summer Bootcamp 2026 Nuclear Next Understanding Fast Breeder Reactors. I'm Gia Bhandari from the Noida campus, and with me, I have Mrigdha Jauhari co hosting today. Today, we will be exploring one of the most significant areas in advanced nuclear technology, which is fast breeder reactors. As the world faces increasing energy demands and the need for cleaner, more sustainable energy solutions, nuclear technologies are becoming an important and pivotal part of conversations around the future of energy. Now, fast breeder reactors, they represent a fascinating intersection of nuclear physics, engineering, and energy policy. Unlike conventional reactors that we learn about, these systems have the ability to generate additional nuclear fuel while producing energy. So, this makes them an important area of research for improving the efficiency and sustainability for nuclear power. To help us understand this fascinating field, we are honored to have with us Dr. Nitendra Singh, founder and president of IYNS Research Foundation. Through his work in scientific research and innovation, Dr. Singh has contributed towards creating greater awareness and discussions around emerging technologies and their role in addressing global challenges. We are grateful to have him with us today and look forward to learning from his expertise and experiences. Thank you so much.
You.
So before the questions start, would you like to say anything?
Frankly, I'm quite excited to take this session forward. Very happy to see the enthusiasm and curiosity about fast breeder reactors and in general nuclear energy. And I remember when we first started energy bootcamp with Shivnadar Foundation way back in 2019, 2020, the momentum seem quite progressing well. So I'm very happy to be part of it. Thank you.
Thank you, sir. Happy to have you here. So, considering how we have so many middle schoolers, let's keep it simple with the first question. We first wanted to, understand what the foundation of nuclear energy is itself. So, as our world becomes increasingly dependent on technologies like AI, electric mobility, digital infrastructure, the demand for reliable and more sustainable sources of energy continues to grow. Now, nuclear energy is unique because of its extremely high energy density where a small amount of nuclear fuel can generate huge amounts of energy. So, for high school students, middle school students trying to understand what nuclear energy really is, what nuclear fuel is, what would you explain as to why the splitting of an atom releases such significant amount of energy compared to burning maybe conventional fossil fuels?
So I think even whatever audience we have, whether let's say it's middle school or high school or senior secondary, all of you understand atom, right? And you understand matter. So if you take note of this, that matter is made up of a lot of atoms. And in 1 cubic centimeter of matter, if you take, whether it's in the form of solid, whether it's in the form of liquid or in the form of gas, you have some atoms into it. Depending on the property of matter, let's say solid will have more number of atoms in this particular volume, while gas will have little bit less number of atoms into this. So in understanding the conventional fuel, let's say you have a gas, which is gasoline, what you put, or petrol, what you put, these sort of fuels, or you can take a fuel like charcoal or wood, which is again a solid material. You burn them and then you get energy. So what is happening there when you speak about these matters and burning or any process of transforming energy, the bunch of molecules are taking part. So molecules are transforming in one form to another, and during this process, this chemical energy is releasing, which is in the form of heat and also in the form of smoke and everything else. So that's how the chemistry of fossil fuels work. So they involve molecular structure. Each molecule have some sort of number of atoms, and this entire molecule is taking part of it. That's how the conventional fuels are working. While in terms of atomic energy, or as we say, nuclear energy, nuclear fission energy is where this atomic structure, one atom, which forms the molecules, this one particular atoms breaks apart. For example, assume you have a single stone, okay? And if you hammer it down, it breaks into two parts. So the stone become two part. It's still stone, but two different part of stone broken. And there are some smaller particles which are also created when you hammer it down. So that's how the process of fission work. When you have uranium-235, which is a particular isotope of uranium, which basically breaks down into two another particles of, let's say, barium and tritium. These two particles, and along with that, some little particles, which we call neutrons, are generated. And also there is some mass which is not converted into any other particle that converts into energy. And this energy is something which we receive. So imagine in this 1 centimeter cube volume, which we were mentioning before, here you will have number of atoms, and these many atoms can undergo fission. So these many reactions will occur. So the number of atoms producing these number of reactions multiplied by the amount of energy one reaction is producing, this becomes huge. While if you compare it with any molecule, let's say you have wood. So wood itself is a complex material. It has carbon, nitrogen, a lot of hydrogen. So it becomes a big molecule. So it's very difficult to, let's say, have this undergo fission. So this entire molecule is shifting. Okay. So that's why the energy in fission or nuclear processes is much higher compared to any conventional fuel. Does it make sense?
Okay, so if it makes sense to all the middle schoolers, could you guys show me a thumbs up? Guys, you could also write in the chat if oh, okay.
Yeah.
So building on what you said, sir, I would like to ask that we know that and we notice that climate change is an increasing, you know, um awareness and conversations that are happening in our generation. So why do you think that why is developing an understanding of nuclear fuel and advanced nuclear technology becoming increasingly more important?
So one thing you need to understand why climate change is happening. So take Earth as a closed system, okay, like a balloon. So we all are covered by this atmosphere. So entire Earth, entire planet is covered by this atmosphere. So amount of carbon forms, carbon dioxide or methane or anything, any greenhouse gas, it is limited within this atmosphere. So if we keep on producing a lot of carbon into it, it gets trapped into it. And that leads to a serious problem because that imbalances the uh, entire ecosystem of the planet. It increases the problems of different level of heat or temperature across the globe, which in turns creates a lot of hurricane, wildfires, and everything that indirectly lead to the acidification of oceans. And all of this imbalance lead to the problem of humanity for the nature, for the animals. And this is not a good thing. Okay. Uh, from where this carbon is coming, it is coming from the energy production. So in our life, if you see, we are speaking over this across the world, over the internet. All of this requires a lot of energy. All these reels, social media you are looking on your mobile phone, that requires energy. These are the direct electricity forms we are talking about, but there are other energies, other places where energy is consumed. For example, your anything what you see in your household system, it is being manufactured in some industry, and that also requires a lot of heat or energy of different kind. So if you notice, the major contributor to this carbon emission to this atmosphere is coming from this energy production. And for this energy production, even today, entire world is relying more upon fossil fuels, which can be oil, gas, and coal, all of this. So in India, we are relying heavily on it, like almost 60 to 70% of our energy is coming from that. And you have seen, like 2 weeks back, when there was a big heat wave in India, there were a lot of fire uh, cases you have seen in the ACs, in the diesel generators across the country. All of this coming from because of this dependency on fossil fuel. So if you want to have something which can provide you this energy, which is growing in demand every day, but does not produce carbon, or let's say does not produce as much carbon as fossils, then that would be the best solution, right? So now you need to understand from where this carbon is coming. So if you see the conventional, let's say coal you are burning, right? So coal is not carbon as a atom. It's a complex molecule with carbon associated, hydrogen associated other molecules, all of it. So it forms a big molecule. When you burn it, it gets it heat. These big molecules, small, split into smaller molecules. One forms the ash, one forms the carbon dioxide. Okay. But again, it remained molecule. Let's say carbon dioxide, CO2. It has three atoms, two atoms of oxygen, one atom of carbon. So it's still a molecule. Okay. So that's how the energy is being produced, and you are receiving a lot of CO2 into it. But if you see this reaction at the atomic level, imagine you have a fuel called uranium-235, which is a specific isotope. So when it absorbs neutron, uranium splits into two smaller atoms, not molecules. So one atom splitting into another two atom, which is, let's say, xenon and barium. And it's no carbon anywhere. You don't see any carbon here in this cycle. So that's why you are receiving a lot of energy, but you are not receiving any carbon. So in any nuclear process, you don't receive any carbon, but you receive a lot of energy. Okay, so that's why the nuclear processes are low carbon energy processes. So they can feed you the demand of energy you need without producing any carbon. So that's why nuclear energy becomes, let's say, pivoting solutions to climate strategies, your energy planning for your developing country, and like improvement your life without producing a lot of carbon. Does it make sense?
Guys, could we have a show of thumbs up? Perfect.
Loving
Any
the
questions you have?
participation. Yeah, if you have questions, please
Jen-
feel free to drop them in the chat.
Yes. All right. Thank you so much, sir. I think with the growing energy demand and how such production of energy is degrading our environment, it's important to have conversations like these. Now, let's move towards what we wanted to speak about in this session, fast breeder reactors.
Sure.
Since we have such a young audience, could you first please explain what a nuclear reactor really is? And then,
Sure.
in regards to that, how a fast breeder reactor differs from a conventional one?
Okay. So first of all, you need to understand what are nuclear fuel. Okay. So there are primarily three nuclear fuel available in the planet. One is uranium, but uranium-235, which naturally exists. Okay. So if you go, you dig out mining, you will get uranium-235 along with mostly 238, which doesn't go fission. So uranium-235 is an atom which absorbs the neutron, split off. So we call it fissile material. This exists in nature. There are other two fuels which we call uranium-233, which can only be produced using thorium. So it doesn't exist in nature. You have to create it from thorium. Second, or let's say third fuel, which is again artificially produced, doesn't exist in nature, is plutonium. So plutonium can only be produced using uranium-238, which absorbs the neutron and produce plutonium. So you need to understand you have three fuels: uranium-235, plutonium-239, and uranium-233. And that defines the type of reactor. So most of the reactors, or as we say, the conventional nuclear reactors or thermal nuclear reactors, they all operate using uranium-235. So in uranium-235 reaction, in the reactions, uranium-235 absorbs the neutron, undergo fission, and then produces a lot of energy. And those neutrons can be absorbed by uranium-238, which is also present in the uranium composition, and it converts itself into plutonium. Okay. The fast reactors, they are mostly operated at the fuel, which is plutonium. So they use plutonium and they use thorium into it. And plutonium undergo fission, it breaks out, creates a lot of energy and neutrons. These neutrons are being absorbed by thorium, and thorium converted into uranium-233. And in India, we talk a lot about thorium reactors, which are not yet there. So these thorium reactors are actually operate at uranium-233 fuel. So they use uranium-233, which breaks again, splits, gives you a lot of energy and neutrons, and those neutrons undergo fission with U-233 as well. So in terms of nuclear reaction, if you see, the difference between conventional reactors, fast reactors, or thorium reactors is coming mainly from the type of fuel you're using. Uranium-235 mostly in conventional reactors, plutonium mostly in fast reactors, and thorium reactors, they have uranium-233. Okay. To give you more understanding how it works, let's understand. Imagine you have wood, a dry wood. Okay. So you know how dry wood work. You start it with a fire, it will start burning and no problem. You get your energy done and in the end you have the ash. But imagine if you try to lit up the wet wood, wood which is, let's say, standing open in the rain and rainforest, and you want to cut it and use it, it doesn't burn. You see, because if it's a lot of water into it, doesn't burn, so you cannot use it. So three fuels, what I mentioned, let's say uranium-235, 239 plutonium, and thorium, they are like the dry wood. You can use them directly to create the energy and you can use the energy. While thorium 232 and uranium 238, they are like the wet wood. You need to dry them before you can use it. So you have to convert them to 233 uranium or plutonium before you can use them. Now, if you see how I can dry the wet wood, I can dry the wet wood by putting it near to the dry burning wood, right? It will continue to dry and then eventually it will dry. You can use it for burning as a fuel. Similarly, in fast reactors, what you do, you put your fuel, which is, let's say, plutonium, and you put thorium and uranium-233 on the sides of it. When there are a lot of neutrons coming out of this fission reaction, they absorb the neutron and convert into 233 or plutonium-239. So that's why converting into the more fuel. So in the same philosophy, if you could burn dry wood and keep the wet wood alongside, you will lose this entire dry wood. It will be consumed, but all this wet wood will get converted into dry wood, which is more fuel. Similarly, when you put your uranium-235 or let's say plutonium-239 in the fast reactors, and you put a lot of thorium and uranium-238 blankets on the sides, this is consumed, giving you the energy, but the neutrons absorbed by those thorium and uranium-238, they get converted into plutonium as well as thorium, uranium-233. So you get more fuel out of it. So this is the philosophy, or let's say processes, which differentiate between conventional reactors, fast reactors, and thorium reactors.
Thank you so much, sir. Just for the middle schoolers to understand, I would like to ask you if you could explain what the different isotopes and the number behind the element actually signifies. As you said, uranium-233 and the different numbers. So
Sure.
could you just explain?
So when we say isotope, before that, any element in the nature, any element what we have in the nature, it is defined by how many number of protons it has in its core shell. So for example, if you say hydrogen as a gas, So it has one proton in its core. But if you say we have carbon, for example, then it has 6 proton in its core. So protons remains the same for the entire universe, but the number of protons defines which element is what. Then to balance out this protons, you have neutrons attached to it. Protons are positive while neutrons are neutral, zero, no charge. So together they form the entire atom along with an electronic system, so a lot of electrons, which balances the charge. So the entire atom remain neutral. Okay. Now, when I say different numbers, so for example, uranium 235, uranium 238, which you heard me saying a lot, in this number of protons, which is 92, remains the same. So that defined that the atomic structure of both the material is 92 proton system. Uh, when I say 235 and 238, that is the combination of number of protons plus number of neutrons. So when I say uranium 235, that means it has 92 protons in its core shell along with the rest of the neutrons. So the total number is 232 protons plus neutrons. While when I say uranium 238, that means it has the combination of 92 protons plus rest of the neutrons, total equaling to 238 neutrons plus protons. So that defines these two as an isotopes. So since the proton number is same, their chemistry, their physical property, everything remains the same. But their radioactivity property or radioactive properties, they vary. That's why uranium 235 undergo fission, it splits and produce energy, while 239, it doesn't undergo fission. It absorbs the neutron and convert into 239. This is the basic difference.
Thank you so much.
I just
Yes,
want to add here, I like that kind of questions flowing in the chat box, Nitendra, and I can see Siddhi and other these moderators, they are continuously replying them. But just for 1 minute, go through all these questions, and children are doing brilliant job. Siddhi and all, continuously they all are replying back. The seniors to the juniors, but still you just go through once, and if you feel that you would like to address, and students, if you would like to address some question which you haven't understood yet, you can write here so that Nitendra sir can address now. Thank you, Siddhi sir. Thanks, Jia, for giving me time to speak.
I see one question. What reactor? What is the reactor? Okay, this is interesting. So for example, as I mentioned that you burn the wood, right, to generate your electricity or energy, not the electricity. You use some sort of place where you put the wood and you fire it, right? Or let's say you have your gas stove in your kitchen. So you connect your cylinder or a pipeline through which gas is coming, and it is being put into this square thingy from which fire is being lit. So if I have to name this device, I would call it a home gas reactor. So the system is where you're putting gas at your home, and reactor is the place where this reaction is happening. So similarly, nuclear reactor is a place where you put your fuel, which is uranium based fuel or any plutonium based fuel or any uranium 233 based fuel, which is where your reaction will be happening. So the place where fuel is there, it will be absorbing neutron, undergoing split, and a lot of energy is being taken out, and you can take this energy out. So this place where this reaction is happening is called reactor. So when we say nuclear reactor, this is what reactor means. And it can be of different sizes. So starting from a small, let's say, small size like a truck container to a very big, like your entire building of apartments. So depending on how large you want to make it, how many houses you want to power, it can be small to large. It can be of different fuel based as we have discussed. So depending on what fuel we have, it can have different name. Conventionally, we call them nuclear reactors, which work on low neutron energy. When we speak about fast reactors, they are primarily using plutonium-based fuels. The neutron energy there is high into the reactions. And if we talk about thorium reactors, the fuel itself is different. It's uranium-233 based. And the definition of which type of reactor comes precisely from the energy of the neutron.
Nitendra, you have question on Chernobyl.
Where? I still don't
So
reach
many
there.
questions on Chernobyl.
Yes, tell
They're
me, what is the
asking what
question?
caused the disaster and why isn't nuclear power banned after the Chernobyl disaster, which I think is an interesting question.
Sure.
Very
So,
interesting.
sure. So now you need to understand the basic before we go to Chernobyl, what happened. So what happened, you have a fuel, which is, let's say, conventionally it can be in the form of pellet. Let's understand like a toffee. I don't know which toffee these days it's popular, but like little candy, like that. And in this solid, there is a water or any fluid flowing around it, which takes out this energy. So in this particular candy, there is a uranium-235. Okay. You started bombarding it with neutron. Once it started, one atom splits and you receive three neutrons. These three neutrons then interact with the three uranium atoms again, and they produces 333, 9 neutrons. And then these 9 neutrons interact with the 9 uranium atoms, which gives you 27 neutrons. So likewise, if you see it's going out, there are a lot of number of neutrons coming in. So if it continues to happen like that, there will be a lot of reactions will be happening. So consider it like again, take an example of wood. As soon as you started with little matchstick, eventually there is a lot of fire because a lot of molecules are burning. So you don't want this to happen in a nuclear reactor. So what you do, when three neutrons are produced from the first atom, you absorb one of the neutron and convert it into another fuel. You let one neutron to continue this reaction, which will produce another reaction in another atom. This will also produce three, but you absorb two and you let only one to do another reaction. So you continuously producing a chain reaction, what we call in the nuclear reactor. And once it started, this chain reactors continue to happen and you continue to cool it down using the water and you extract this energy. Imagine a situation that this reaction is happening, but your flow of water is not happening. So there is no water, but reaction is continue to happening. Energy is going out. You cannot take this energy out, but its energy is being produced all the time now. So eventually what will happen, it will dry off the entire core. There will be no water to cool it down. The temperatures will be high, which will melt this candy down.
One sec. Siddhi, could you
And-
please,
Yes, ma'am.
whoever is the
I've
host,
just muted.
mute everyone
And-
except Nitendra and
Yes, ma'am. Yes, ma'am. I'll just do that.
So as soon as you have this high temperature because of this energy is not being taken out, this candy will melt. And once this is melting, it will go down and it will be difficult to manage. So in Chernobyl was not the conventional reactor. It was a military kind of reactor, which has different perspective. and there they were testing this safety mechanism. So they took off the safety device. It's like you want to test a system. Let's say there is a wall and there is a person working on a ladder on this wall. Now you want to test that if we remove this ladder, whether this person will fall or not. So eventually, to test it, what you did, you removed the ladder and person actually fall down. So the similar thing happened for the Chernobyl, that they wanted to test this safety system. So they switched off the safety system and let the reactor go in the accidental scenario, and this eventually led up to have this accident. But this is the time we are talking about long back, where people were learning to develop more of the safety systems. So that's what happened in Chernobyl. A lot of reaction continued to happen. There was no water to cool it down, and the number of neutrons started happening, and there was no safety system to block it. So that's why Chernobyl happened. But this is not possible in, let's say, modern days reactors, because you have a lot of safety systems and they cannot undergo that sort of situations now. And there are no dedicated military reactors which are working on that design which was there in Chernobyl. Does this make sense?
Yes. Thank you so much for simpling down this
I
disaster
am
for
trying my
us.
best.
Yeah. Also, could we also request all of the students to please be respectful in the chat box? Moving on with the question, sir. We have something related to what you just explained about the safety domain of it. Safety domain is one of the biggest considerations in nuclear technology, and over time, reactor designs have evolved significantly through research and lessons learned from previous experiences. So, how have nuclear safety systems evolved? And how are modern fast breeder reactors designed to ensure safety operations and manage potential risks?
Okay. Nuclear industry is very different from any other industry in the world. So we keep on learning from all these mistakes and all these ideas, what is going. Okay. Now the safety systems what we are working on, or let's say have already been imposed in the advanced reactors or new reactors, they don't require any operator's intervention. So for example, let's take the example of Chernobyl itself. At Chernobyl, what happened? There were operators who switched off the safety system to conduct those experiments. Okay. What happened at Fukushima? There was a big wave of water came in, which flooded the entire reactor site, and there were no operators who can actually switch on or off the safety systems. Okay. So now this we understood that this is possible, that even in future, if that sort of scenario comes in, there are no operators who can switch on and off or operate these safety systems. So that's why all these new reactors, or let's say the advanced reactors, they work on the safety systems which we call them as passive safety systems, which is like let's say back to the basics. So if I ask you a question, that you have a water tank on your, let's say, on your roof, and if you open the tap of this water pipe connection, which is connected to the roof, what will happen? Anyone take a chance?
Would anyone like to say anything in the chat box? Any questions regarding this?
If no, then I'll simply explain.
I think
There
one
is
of
a
the
boy who
students.
is raising hand.
Yeah.
Harmans. Yeah. Please unmute and speak.
Ma'am, I have a question. I have two questions. Do proton act like waves?
Could you please repeat?
Do proton act like waves?
They do.
Okay. And my
Yeah.
other question, how fast is a proton?
I'll come to both of these questions in a minute before I complete this first part, okay?
Okay.
But I
So,
really like this question, Nitendra. This child,
yes,
which
it is
class you are
interesting.
in? Which class you are in?
6.
Interesting. Okay,
Cool.
thank you.
So,
Over to you,
what I
Nitendra.
was mentioning about the safety system. So, imagine you have a water tank at your roof, and if you open your tap, the water flows down with the gravity. You don't need anyone to do anything. So all these new reactors have something like this, which we call them a safety, passive safety systems. So passive means you don't need to do anything. Gravity will do something, or let's say the physics principle will do something. Another example, if you have, let's say, a water, one at the base, you start heating it up. So eventually this water which is at the base, when it heats up, its density become lower than the density of water which is at the top, which is cooler. So they start working going up and cold water start coming down. And this continue the process in a cycle because of this temperature difference. And again, because of the gravity, because high density, gravity pulls it down, lower density, this goes up. So all of these are happening on their own. It's the simple physics which we are talking about. So new reactors or advanced reactors, including the fast reactor, they have a lot of passive safety systems. So they operate without any operators requirement. They can take care of the reactor accident scenario and bring the reactor at the safe state without leading to any situations like Chernobyl or Fukushima, what has happened. So that's why these new reactors are much more safer and much more easy to operate. Now coming back to the question of proton and wave. So all matters, including humans, they all can behave as wave or particle, depending on your speed. So proton, if it is at high energy and high speed or high velocity, it can behave as a wave as well. Or us as human, if we could, like say, speed ourselves to a speed of light, we can behave as a wave as well. But since we are slow, that's why we behave more into particle fashion. Now, how fast these neutrons are? So the term is very technical. Fast means high energy, and we measure the energy in terms of electron volt. But I can tell you in this fashion, the neutrons being produced in a reactor which is splitting the uranium, the neutron energy is about like they can reach to the moon from the earth or from that reactor in
Yes.
about 26 27 seconds. So that fast is the neutron. So it's close to the speed of light, not exactly speed of light, but it's really close to the speed of light. That's how these fast neutrons are. And depending on type of neutron, we slow them down to be used in the reaction, atomic energy or nuclear
You can
reaction.
see the chat box is flooded with questions. I really like, and the whole idea was to ignite students and to ask questions.
Sure.
Yes, ma'am, the enthusiasm is great to see. Even Harman's question, what he asked is something that we're learning now in 11th grade. So I think we'll keep it short. We'll ask you one final question that is in regards to what the students would favor, and then after that, we'll open the floor for questions from the students directly.
Sure.
So, for students who are joining us today who are interested in contributing to fields like nuclear science, engineering, and energy research, what are the certain skills or areas of knowledge, or maybe even mindsets that you think they should begin developing from their age?
So I would say the excellence in whatever you're learning is something you need to focus on. So for example, if you take one nuclear reactor, okay, which is producing a lot of energy, there are all type of engineers there. There are mechanical engineers, there are civil engineers, there are electrical engineers, electronics engineer, instrumentation and control, safety, There are chemists, there are biologists, there are health and safety, there are doctors who are treating them, there are firefighters, there are cleaning staff, there are maintaining staff. Everyone you can think of are there. There are physicists, there are mathematicians, there are accounts people who are taking care of all of this. There are business people, there are MBA people. There are people who are doing geology and geography analysis for the reactor deployment. So any field you imagine in your life, people are working there together with different specialization, different skill set, which you will learn as you grow. So instead of like, if you want to work in a nuclear reactor, I have to study physics only. That's not the only criteria. You can become part of nuclear industry by anything you want to learn on, but you have to learn the best. You have to really focus on what you are learning, not just like you get the degree, but you don't know anything, you somehow pass the exam. That won't help you in life. But if you really understand the basic, you really understand what it is happening and why, it will take you to anywhere you want. And it is not limited to nuclear fission energy, it is also for fusion energy, which is, let's say, the even advanced version of nuclear era we are going to now. So all of this requires different and diverse type of skills. So your excellence is important. Second thing, which is additional to this, not only don't focus only on one part, try to learn as much as you can from the surroundings. For example, I have seen students, those who are in science grade, they focus everything on science. They don't know anything about arts or aesthetics or what it is. So, and the people who are studying arts, they don't know anything about science. They are afraid of maths and everything. Don't do that. That won't help, because eventually when you grow in life, you will reach to a point, not very far, like very soon, where you have to address both of them in either field. So it will be nice that you keep yourself aware from the other aspects as well. So focus whatever your interest is, but keep everything in the surrounding and keep learning that part as well.
Thank you, sir. Definitely. An interdisciplinary approach is so important nowadays.
Indeed.
Yes. So thank you so much for sharing your insights with us and really helping us understand this field that seems so complex, even to us as grade
Pleasure.
11 students. You did such a good job at simplifying everything. And
Thank you.
today's discussion, it really showed us that, nuclear science isn't just about learning about reactors. It's about solving a lot of challenges that we face as humans in energy consumption, sustainability, security. So before we open the floor for questions from students, we'd like to invite Mayank sir from Vidya Gyan. Mayank sir, if you could speak a few words to the students, that would be great. Do we have sir with us?
Or Rachna ma'am also can do.
Oh,
Oh,
sir.
Am I audible? Yeah, so
Hi, Mayank.
thanks,
Good
sir.
to see you.
First of all, good evening. I was not at all prepared. I was not expecting I'll be being called. So first of all, I'm sorry. Still, children, I could see some of the questions in the chat. So first of all, Nitendra sir has done, like, no one can be better in comparison to Nitendra sir for explaining the concepts which have been given to you. So as you'll move in your higher classes, just maybe in class 8th or 9th, you'll study about subatomic particles, electron, proton, neutrons. And basically at that time, you'll come to know that electron revolves around a nucleus. And inside the nucleus, there are proton and neutron. So that is what was being discussed. I see lots of questions were related to proton and neutrons. One thing more, which personally I would like to share, credit to Nitendra sir, Vinita ma'am. Recently, I got an opportunity to visit one of the finest nuclear lab of India, that is Institute of Plasma Research. Children, one thing which I can see, whatever you are studying in your classroom, whether it's mathematics, physics, chemistry, and as sir said, each and everything that you're studying somewhere contribute in your future. At the same time, whatever you are going to design in, whether you're going to become a physicist, a nuclear scientist, everything is going to help you. So study with love. Study with emotion. Everything somewhere or another is going to help you a lot. Keep this in your mind and enjoy your studies. Literally, it makes the world more beautiful. Later on, when we are leaving also the planet, it will be much more beautiful in comparison to what we got it. These people, Nitendra sir, Vinita ma'am, they are making the planet the best place to live in, truly. So all the best. It's sincerely a blessing to interact with these people. Enjoy it. I can see lots of hands. Over to you all, children. Take the best advantage of the finest scientists that we have on the planet. Yeah.
Thank you, sir. Thank you
Thank you.
so much.
Thank you so much, sir, for your sweet words. Now, we would encourage everyone to take this opportunity and students to engage, clarify their ideas, and explore their fascinating field further. Please raise your hand virtually in the meeting and wait for your name to be called before asking your questions.
We have 15 minutes. So, and there's so many. So, what I suggest, Ria, please copy paste all questions also and keep it in our record. We will answer all these questions. We have this kids' email ID. They have registered for this. Yeah, you can ask few questions. Students, you can
Also-
raise your hand and ask. Yeah.
Yes, also after the meeting, we'll also send you the recording of the session as well as a Google form if you have any questions. Then you can enter your questions there and we'll relay them to sir and then get back to you with the responses. Okay, I think we can go ahead with the questions. Jia and Mrigdha, you can start picking people.
For sure. So just another point to note, in case your question does not get answered today due to time constraints, you can always reach out to Vinita ma'am, both of us, or Siddhi, or the Carrier Society as a whole, and we'll help bridge the gap between you and Nitendra sir to answer your question. So starting off, we want to start with our Bhargavi. So if you could unmute and ask a question.
So I had a question. Do neutrons have voltage? And if they do, how much? Because Sir mentioned the power of the neutrons is pretty high. It can literally jump to the moon and come back in 20 seconds. And that's a lot. So I was just wondering what exactly powers it? If it's not voltage, then what is it?
So it's more of a kinetic energy it has. So for example, when it's coming out of this reaction which is happening between neutron and uranium, the internal process, it becomes like a big bulky neutron proton cloud, and then it breaks apart. So when it breaks apart, all 5 elements, 2 radioisotopes and 3 neutrons, they get a lot of kinetic energy. So this energy which was trapped inside converted into kinetic energy, and this kinetic energy is what we are talking about. So this kinetic energy helps it to reach to the moon if it is not stopped. So you can measure this kinetic energy in terms of joules, in terms of electron volts, in terms of power. This is all up to you in whatever unit you want to convert it. But precisely, this is the kinetic energy here we are talking about.
Okay. Oh, and I also wanted to say it was very relatable.
Thank you.
It was
Which
a wonderful
class and
question.
which campus you are?
I'm in Faridabad campus.
That's great.
Okay, moving on, we'd like to invite Deepa Kakkar to ask the question.
Tell your school campus name and then you ask question.
I am from the Faridabad school campus and I would like to ask the question, what if the water pressure is so high that it breaks the safety system?
That's very interesting question. That's my kind of question. So when we know what sort of pressure we need to maintain while designing the safety systems, we also calculate at what pressure it can break down. So when we are designing our pipes or our systems, we make sure that we design it after this pressure which it can break up. So for example, due to any region, let's say the pressure is increasing, and even if it is reached to the pressure where it can break, we make sure that we have additional thickness to these pipes so that it doesn't break in any circumstances. Assume even if it breaks in at that safety margin, we always have another safety systems which can take care of it. So in nuclear systems, we design multiple safety systems, which we call defense in depth. So as you go one after the another, there is second, there is third, or let's say there are four safety systems, which are attached to it to make sure of any extreme it should go on. So that's why we call it safety margin. So for example, if you're designing your system to be operate at, let's say, 100 bar, you design your system to take care of 150 bar, and considering that, you can take care of all the pressure increase in this safety system.
Thank you, sir.
Hope that
pleasure.
answers your question. Can we ask Kanika Sehgal to please address your question?
So I had a question. So basically, this session was kind of about FBRs, but what is the point of using them when they use so many resources and produce only one more type of fuel? Why can't we just use traditional reactors?
So first question, like what sorts of resources you are thinking that they use more? Because I have never said they use different resources or more resources.
So when I was researching about this, it said that FBRs used more coal or something like that.
No. So I tell you what is difference. When we do the conventional reactor, okay, there the fuel amount is less. So for example, in the conventional nuclear reactor, the total amount of uranium-235 is about 5%. So for example, if you're using 100 kilo of fuel, so uranium-235 will be only 5 kilos. While in terms of fast reactors, this amount of fuel is higher. So for example, if you're using 100 kilo of fuel in the fast reactor, the amount of uranium-235 or plutonium will be about 20 kilos. Okay, 15 kilo, 20 kilo, 10 kilo, something like this, higher than the conventional reactor. But when you finish your cycle and the thorium and uranium-238 blankets which you put, they absorb a lot of neutrons. The amount of fuel which they are producing in the end of the cycle is, let's say, more than 20 kilos. Let's say 30 kilo or 50 kilo. So for example, if you have put 20 kilo, you are receiving 40 kilo. Even after utilizing this fuel, getting a lot of energy out, and you're getting a fuel as well to fuel it afterwards. That's the benefit of having the fast reactors. While in conventional reactors, if you put 5 kilo and it continue to use and produce energy, it uses about 3%. So let's say 3 kilo it used. It left with only 2 kilo of fuel and we use the energy. So we are not getting anything in the end after this.
So
So
what is the
that's
point of making SMRs when we already have FBRs?
SMRs is different technology. So in SMRs, you are not doing breeding mostly. So SMR is a small modular reactor. So you have, let's say, reactor which can produce 300 megawatt of electricity and more. They are called large reactors. And the small reactors are which can produce energy from 50 megawatt electric to 300 megawatt electric. So SMR can be a fast reactor as well. So small reactor which can do this fast reactor in breeding can also be called a fast reactor. So fast reactor is a type of reactor which utilizes fast neutrons and reproduce or breed more fuel. That is called fast reactor. SMR is the size of the reactor what you are referring to. So this is two different things. So SMR can be a fast reactor, SMR can be a conventional type of design of reactor, and SMR can be a thorium reactor as well.
Okay.
Okay. So moving on to the next question. Can Harman ask his question?
How many types of atoms are there?
Atoms are, as far as we know, only one type. So they have protons and neutrons together, and different number of protons and neutrons combination creates different types of elements. While the atom type remains the same, which are made up of protons and neutrons. And protons and neutrons are also made up of quarks. And there are again definite set of quarks which produce protons, and another definite set of quarks produce neutrons. So the atoms remains the same for all of them, for everything.
Okay. I thought there were different types of atom variations.
No, when I was kid like you, I used to think the same. But eventually, these atoms, when they combine with another atoms, they form different things. To give you better understanding, if you have one atom only and it has only one proton, it forms hydrogen. But if you have another atom which has a lot of protons and a lot of neutrons, it forms another atom which is more heavier, but the atom becomes more of an element of different kind. And when you have these different type of atoms together, they can form different type of elements and different type of molecules. And then those molecules define what sort of matter it is becoming. So for example, with similar atoms, you can form gas and also solids and liquid. And those similar atoms can behave like wood. And these similar atoms actually forms people or human or living life like us.
Thank you.
Sir, so moving on to, I think, the final question for today. Before that, sir, when you answer the next question, could you also speak briefly on what Harman had asked before, if protons act like a wave? You said you'd address that later. And if we could take Aryan Mathur's question now, that would be amazing.
I think Sir had already addressed the wave question, right? Right, Herman?
Yeah, with the speed.
Like when can my question get answered?
Just one second. Who had you called out? Mrigdha and Jia right now?
Who?
Aryan Mathur.
Okay. We'll have your question be the last one after Aryan Mathur, okay?
Okay. Thank you.
Perfect. Okay, let's go.
So, sir,
Yeah.
so you know the nuclear reactor, right? So are they connected to nuclear bombs? And if they
Not really.
are they connected to nuclear bombs? In and a
Not
bit.
really. Sorry, complete your question. Your question, which
I said then are the nuclear reactors connected to nuclear bombs? Because they both have the word nuclear in their name.
Can I answer, Nitendra, with your permission, and then you explain?
Sure.
So it's a very interesting question, and seeing your grade and such inquisitive mind, I'll only say that it's something like you cook food on gas stove, right?
Yes.
So you see the flame, the temperature, and exact amount of flame. But
Yes.
imagine if that cylinder blasts and the kind of fire comes out, and obviously when you cook on gas, you are controlling it. Sometimes you are making sim, sometimes you are making high, required for the food. So it's a controlled fuel coming out. Okay. But if there is a blast in cylinder, then it will be a big, huge amount of fire, which is disastrous, right?
Very different because it is an electrical fire.
Yeah, or the gas cylinder blast, it will be huge amount, and which is uncontrolled. You can't control at the time of blast. So I think I just want to relate it with that when we say nuclear reactor, how much energy we want in a very controlled fashion, we take that much energy so that there is no kind of blast type of scenario. However, when we say nuclear bomb, the chain reaction, what Nitendra sir was explaining, or even the fission or fusion reaction, they are uncontrolled manner. So huge amount of energy comes out, and that is disastrous. I wanted to explain in a very layman.
Sure, ma'am.
So
I want to add a bit more. So why we call nuclear? You said both of these term has nuclear.
Yes.
So we call both nuclear because the reaction it is happening is nuclear reaction. In both the cases, fuel, which can be uranium or which can be plutonium, it absorbs the neutron and then undergo fission, producing energy in both the cases. But what is the difference is the amount of fuel we have in two different devices. So when we create a reactor, we have a lot of structural material, a lot of water, a lot of everything, and the amount of fuel is only 5%. Okay, or let's say
Hi, yeah.
maximum 20%. Okay. But when it comes to a bomb, when you want to use it for a military purpose, you use smaller device with a lot of fuel. So amount of fuel mostly goes more than 80%. So that's why a nuclear reactor cannot become a bomb. And that's why these two are completely separate. To give you another example, let's say you have a balloon, and in that balloon, you put, let's say, half kilo of gas. But in the same balloon, if you put like 5 kilos of gas, this gets blasted. So it is the amount of fuel which you are putting in, which defines it whether it will uh, become a bomb and become a reactor, and also how you put it. So in the bomb, you put everything in a compact fashion, while in reactor, it's very loose fashion. You put a lot of pallets here and there in an organized but distributed fashion, while in bomb, you put everything as a compact volume.
Hope that answers your question.
I hope so.
Yeah, thank you so much, sir. Last
You
final
said my question was last.
Yeah, just coming on to you.
Okay.
Could you go on with your question now?
Okay, so India has successfully achieved to create a smart breeder reactor. Can you like explain about that in detail?
So as I understand, you want to understand about the fast breeder reactor which India has recently got critical.
Yeah.
Okay. So see, we need to understand what are the challenges India has. So India don't have a lot of uranium resources. So that's why we cannot expand our nuclear program just like that, because we need to have a lot of uranium to be put in those lot of reactors. So that's why we need to find some solution to that. So solution to that is we have a lot of thorium. So if we could breed thorium using this uranium, what we have, then we can produce a lot of uranium 233, which will be our own fuel, which can power a lot of expansion of nuclear power plant. To breed this thorium, as I was mentioning in the beginning, this example of wet wood and dry wood, we need to put this thorium into a fast reactor where they can absorb this neutrons coming out of this uranium or plutonium based fuel, which we got from the other reactors which India is already operating. And then we can produce a lot of uranium 233 out of uh, thorium, which can be used for India's advanced thorium reactor. So this fast reactor, which is FBR, is based in Kalpakkam in Tamil Nadu, which is of capacity of 500 megawatt electric, and it can produce, and it is operating with the advanced nuclear technology India has, and it's a big achievement in that sense. And now India will produce similar reactors in numbers so that we can do this process of thorium breeding as fast as possible, so that we can rely completely on our own uranium 233 resource for powering the nation, I would say.
Thank you.
Pleasure.
Before we end, could we have like
a show of thumbs ups and just clapping reactions for Sir for
Thank you.
explaining so amazingly.
And also, if we can have one picture, if at least half of the students, open the camera.
Yes, please.
Yeah.
Everyone, please turn on their cameras.
Yeah, we can click a photo and
All right, let's keep the applause going. 3, 2, 1. Perfect. I got it.
Thank you.
Amazing.
A little bit, if you can stay for a minute.
Yeah,
Yes,
Jia and Mrigdha, could you conclude?
Yes. So to conclude, first of all, we want to extend again our sincere gratitude to Dr. Nitendra Sir for being here with us today. Thank you so much for explaining with such conviction and simplifying everything for us today. And we also want to thank Vinita ma'am for being the pillar behind this, and of course our student lead Siddhi Kochar for helping us plan everything for the KaryoUS Bootcamp. Okay.
And Rachna ma'am and Mayank sir and all the lead teachers who are present in the evening, along with you all.
yes.
The
So if any
audience.
questions that we could not address today, please feel free to reach out to Vinita ma'am or the organizing team, and we would be happy to help bridge the conversation further. Thank you everyone for joining us. And we
Yeah, if you could just explain in 1 minute, or Siddhi, that what is our next session on, which children will be very excited, because that's much more simpler and very relevant.
All right.
Siddhi?
So, yes. So for everyone here, we understand that this session might have been a little bit complicated. We did learn a lot, and I'm sure it sparked a lot of curiosity in all of us. So the next session is going to be a very interesting one. How many of you know what radiation is? Can you have thumbs up? Okay, we have a lot of raised hands, a lot of thumbs ups as well. So we know what radiation is. Some of us might even know how it came about. But the next session, we're going to have a guest who's going to address what are the pros and cons of the radiation around us? Is the radiation around us actually helpful in some way or the other? Or is it actually harming us in ways that we don't know of? And radiation, all objects possess some sort of radiation. For example, even our mobile phones and the things that we carry on a daily basis. So it's very important to know why these things are important, and why whether radiations can be harmful or beneficial for us, and in what context. So it's going to be another such engaging session about that. And yeah, Vinita ma'am, anything you would like to add?
No, that's it.
Okay, perfect.
And
All right.
will be taken by Dr. Samyak Munot, who has done his research and all in Bhava Atomic Center, and the Vice President IYNS. Thank you.
Yes, and the link for that and the registration link for that session will be given to you in the same way that it was for this session, by your own individual campuses, and then you can register from there for that session to get the Zoom link after that.
For all the people who are still raising their hands, Siddhi is going to be sending our email ID on the chat box. It's team.noida@sns.edu.in. Even though it says Noida, it's for all campuses. So through that, we can communicate your questions to Sir, and maybe send you a document of common questions that you guys have asked and the answers to them. I hope you guys enjoyed today's session, because we really enjoyed having you here. All right. Thank you so much, guys.
Have a great day.
Thank you, all of you.
Bye-bye.
Thank you so much, sir.
Such a pleasure. Thank you for the information, sir.